Hey y'all, welcome back. Let's dive into this sinusoidal modeling homework. So these first two problems have no context. They're not word problems like the rest of these, just kind of getting you ready to do some graphs here. So it says sketch a graph of the functions, label the scale and axes, just like the way we would normally do it. So let me start by actually drawing out my little window here. Y'all know I like these little window pane. Okay, so let's sketch these out. I'm just doing a quick little grid. So just to kind of explain what I'm doing here, I'm making a little 2x4 grid to help my graphing out. And what I'm going to do is first identify which picture I'm going to have. Is it a positive sine, positive cosine, or a negative one of those? Okay, so this first one is a positive sine graph. So I know that my graph is going to start at equilibrium. It's going to go up and then come back down. Oops, let's make that a different color. There we go. Going to go up, come back down like this, okay? So there's your positive sine curve, and then I might as well, while I'm at it, do the negative cosine curve that I see in letter B. I'm going to just kind of do these at the same time, just to really showcase that you're doing the same thing, no matter if it's sine or cosine, positive or negative. The steps that you're taking to graph it will be identical. So this is going to be a negative cosine graph. So instead of starting at a maximum, we're going to start at a minimum. And we'll work our way up and draw like a little hill here. Okay, rather than the parent cosine graph whose first period is more of like a valley. Okay, so this will continue on in both directions. Kind of forgot my arrows over here. Okay. So we've got these two graphs. Now what do we need to do? We need to actually label everything, right? So in order to label everything, we are going to find, we're going to identify all these characteristics like, I like to start with vertical shift, just because that's the easiest one to do. And the vertical shift here is going to be 3. Okay, the vertical shift over on part B is going to be 0, because notice how we're not adding anything. So just to be clear, our vertical shift is this number right here. Okay, whatever constant you're adding or subtracting, that's going to be your vertical shift. And when we go to label the graph, we will label the horizontal equilibrium line with whatever the vertical shift here is. So in this case it'd be 3, in this case it'd be 0. The next thing I like to do is look at the amplitude, which will be the absolute value of A. Okay, so you're looking at the coefficient of the function, which is this number right here, and take the absolute value of it. So if it's positive, it stays the same. If it's negative, like it is over here, it'll change to positive. So in this case, the amplitude is 2, and in part B, the amplitude is 3. Amplitude. Make sure I can spell there. And so what that tells us is the distance from equilibrium to the extreme. So I'm going to add 2 to find my maximum, and I'm going to subtract 2 to find my minimum. For part B, I'm going to add and subtract 3, because that's my amplitude. So 3 and negative 3. The next thing I want to do is identify my phase shift. So that's going to be like, what does the cycle actually begin? It's going to be C divided by B. Notice my B value here is just 1, so it's just going to be C in this case. So my phase shift is going to be, let's see, let me get a little pi here. It's going to be pi over 4. Now, one thing to keep in mind is the way that this is set up. This equation is bx minus c. So the c value here is positive, and that's the only parameter that is going to have the opposite value of what you actually see in the graph. So in this case, c is actually positive pi over 4, whereas over here, the c value is negative pi over 2. But the way we calculate the phase shift is we do c divided by b. Okay, so the c is negative pi over 2 divided by 2 would be negative pi over 4. And then, so that's going to be where our windows begin. So we can actually label that here. Here's pi over 4. So that means over here my y-axis is going to be kind of over here somewhere. And then over here my phase shift is negative pi over 4. So my y-axis is actually going to intersect my cycle somewhere. Okay, once I know what the period is, I can figure out where it's going to be exactly, but we know it's going to be somewhere to the right of over here. So speaking of which, let's look at the period. The period is calculated by doing 2 pi divided by b. So in this case, 2 pi divided by 1 is just 2 pi. Okay, and over here, the period would be 2 pi divided by 2. So the period is just pi. So be careful. Don't label the end of your cycle 2 pi or pi here. Okay, the end of the cycle is not the period. The period is the length of time it takes to complete a cycle. So to find where the cycle ends, we have to take the phase shift and add the period. So let's just do a little side math here, little sidebar. So let's do pi over 4, which was our phase shift, plus the period. Okay, so plus 2 pi. Now, in order to add these two together, I need to find a common denominator. Okay, so common denominator being 4. So I'll have pi over 4 plus 8 pi over 4, which is equivalent to 2 pi. And so we got 1 pi over 4 plus 8 pi over 4 is a total of 9 pi over 4. Ooh. There we go. So that means that our cycle will end at 9 pi over 4. All right, yeah, so that's it. The only thing left to do for this one is to throw on the axes, so might as well do that right now. Looks like my x-axis is going to be somewhere down here. Right? It's going to be below 1, and then my y-axis is going to be somewhere over here too. So this is going to be kind of moved up and to the right. Yeah, so there you go. There's your cycle. For the next one, the period is pi, so I'm going to do a little bit of scratch work over here as well. I need to add, in this case, negative pi over 4 to the period, which is just a single pi. I still need a common denominator here, so negative pi over 4 plus, in this case, 4 pi over 4, and that would give me 3 pi over 4. So this one will be pretty clear where the y-axis is going to be, now that we've found where the end of the cycle is. 3 pi over 4. There we go. So x-axis, pretty simple to figure out where that is, just where 0 is. And then to find the y-axis, like if this is negative 1 pi over 4, if this was 0, 1, 2, 3 pi over 4, that indicates that our y-axis is going to be right here. Okay, so there's number 1. We've got the total graph down, we found all the characteristics, and we're good to go. So this kind of process of finding all of these is what we're going to do with the modeling as well. It's just we will use this to figure out the A, B, C, and D. And instead of pulling these values from the equation, we're going to pull them from the actual problem. Okay, so that's it for number 1. Let's go on to number 2. Number 2 says a mass oscillating up and down on the bottom of a spring can be modeled using a sinusoidal function. At time equals 0, the weight is pressed upward as much as possible and then released. So that means we're going to be starting like at the maximum displacement. When the mass is at its lowest point, it's 10 centimeters below its highest point. That tells us that the amplitude is going to be 5, as you can see from this little diagram here. It takes 2 seconds for the mass to move from the highest point down to the lowest and back to the highest point. So that's going to be our period. So as you're reading these problems, you really want to be taking note of any numbers that they throw at you. Really try to understand what the behavior of the object is. So for example, it's saying at time equals 0, the weight is pressed upward as much as possible and then released. So we know we're going to be starting at a maximum. And then it says, this information is telling us about the amplitude, and then this is talking about the period. So let's kind of sketch our graph here, and then we'll try to break down all the different characteristics. So this is kind of the strategy I like to use, is first let's draw our sketch with all the pertinent information, and then we'll use that to figure out what the A and the B and the C and the D and all that good stuff are. And then finally we'll write our equation. So here's my little grid, And we're going to start at a maximum because it says at time equals 0. So when time is 0, the weight is pressed upward as much as possible. So we're going to start at a maximum. And then when we release it, the mass is going to go down and then eventually go back up. So we get this nice little cosine function here. And once you have it actually graphed, once you've understood the path of the object, or kind of get an idea of what is going on with the problem you're working with, it will help you decide, like, is this going to be a cosine, is this going to be a sine, is it going to be positive or negative, and just gives you a little bit more information about what your function is going to look like. Okay, so from here we can see we're going to have a positive cosine graph, meaning our a value will be positive. We can see here that our equilibrium is going to represent when the object is at rest. And then it gets, the amplitude here is 5, so we're going to label this with 5 and -5. And it says it takes 2 seconds to go from the highest point to the lowest point and back to the highest point. So that's going to be our period. So we've got this all labeled out, and we're going to use this to help us figure out A, B, C, and D. So I'm going to make a little answer box for me here. We're going to figure out what is A. Oh, let's make that red. Oh, what? Okay. A, oh gosh, come on. Red. There we go. So A is going to equal something. B is going to be something, although we'll do that, we'll calculate that last. And we have C and we've got D. So the 4 characteristics, the amplitude, the phase shift, the vertical shift, and the period, are what we're going to use to figure out what all these values are. So I'm just going to move this up a little bit, make this a little bit easier to read. Oh, I grabbed more than I wanted to. I don't know why it's grabbing all that other stuff. I guess I'll move that separately. You guys are, come on now. There we go. Jeez. Okay. All right. So yeah, let's break this down. So our vertical shift is going to be right here. Okay. Remember, equilibrium is where you end up after your vertical shift, and since it's 0, we know that our D value is 0. I like to find that one first, just because it's going to be whatever number is right here. The amplitude here is going to be 5, but we want to be careful. We want to make sure that we put the correct sign on there, meaning we want to know if it's positive or -5. And since we have a positive cosine graph here, since we started at a maximum, we know our A value is going to be positive. The B value will do last. The C value, I think, is going to be 0 on all of these. We might come to one that's not 0, but there's no phase shift here. We're starting the scenario at t equals 0, where when the weight is pressed all the way at the top. So C is going to be 0. And then to calculate B, we need to go back and remind ourselves, how do we actually compute the period? Okay, so the formula for period is going to be 2 pi divided by B. And we know the period, in this case, is 2 seconds. And so we'll solve this equation for B to find the value. So B, so 2 pi is going to equal 2 times B. And we'll get that if we multiply both sides by B. And so here we can divide both sides by 2, and we get B equals pi. So that's my B value right here. And so now I have everything I need. That's all I need to write my equation. So I can go ahead and write it down here. We'll call this y equals, my A value is 5. This is going to be a cosine function. My B value is pi. Let me grab that. So pi x. And then my C and D are both 0, so I'm just going to close this function out. And there you go. There's your equation. So that's it for number 2. See if it'll let me box this. There we go. All right, yeah, there you go. Okay, so that process of sketching out the graph, using it to find your characteristics, and using the characteristics to find the parameters, use the parameters to find the equation, that process is what we'll do for all of these. We just got to make sure we read the problems carefully. But what I'm going to do is I'm actually just going to copy and paste all this because the process here will be the same for all of these. So there's not going to be really any difference in these. So let me just bring the rest of this down. And I'm going to erase some stuff I don't know which function I have, so I'm gonna erase this. I'm gonna erase all these numbers, so I don't know what those are yet. Definitely don't know what the values are, but what I'm gonna do here is I'm basically creating, I just wanna get rid of that red little dot there, there we go. I'm gonna create a little template that I can use for all these problems, so I don't have to retype this every time. Okay, got all that. Now let's delete everything that we don't know yet. Get out of here, menus. Yeah, we're not going to know what that number is yet. Okay, and then we'll just delete this whole thing. Okay, so what I'm going to do here, just to make this go by a little faster. I guess I didn't need to record all this, but sometimes it's just easier to let the recording go. All right, so I'm just going to copy and paste this over and over again. And I guess what you can take away from this is that we're going to work all these problems basically the same way. So it'll be nice to have a little template here for all of them. Okay, so let's go back up to the problem we're at. We did that one, so we're on number 3. Number 3 says Josh and Emily ride a Ferris wheel at a carnival in Austin. When the ride starts, they're at the bottom of the Ferris wheel, so we're going to start down here. It's got a 16-meter diameter and turns at 3 minutes per revolution with its lowest point 1 meter above the ground. Okay, so a couple of things to note here. I'm going through this. It's got a 16-meter diameter, meaning like not the radius, but the diameter from the bottom of the wheel to the top is going to be 16, right? And it says the lowest point is 1 meter above the ground. So here's the ground, and it's 1 meter above the ground. So, if we're thinking about the actual heights here, the ground will be 0. That'll be kind of like our x-axis here. And then the bottom of the wheel, so really the bottom of our rotation here is at 1 meter. And then the top, since this diameter 16, 1 plus 16, will put us at 17 up here. So I want you to think about, well, where's equilibrium going to be? It's halfway between 17 and 1. Half of 16 is 8, so it'll be 8 above 1. So our equilibrium here, like right here, will be at 9 meters. So just give you a little more context around what where your height is at every location. Okay, it also says that it turns 3 minutes per revolution. That is going to be our period right there. And it looks like I've lost my black box here, so let's throw that back in there. Yeah, I don't know, that's weird. Okay, so let's start labeling everything that we have. It says t equals 0 represents the low point on the wheel. So the way that's going to be a little different from the last one is since we're starting at a minimum, our a value will be negative because we have a negative cosine graph. All right, so just make a note that your a value will be negative here when we go to actually take the amplitude into consideration and whatnot. But so here's time equals 0. And then it says it takes 3 minutes for the revolution to occur. So this should be over. We should be back at the bottom after 3 minutes. Now this is where it gets a little tricky. Over here I think it was a little bit easier, a little simpler, especially given they give us a diagram right here to really clarify everything. But on this one, we're going to use these 3 numbers. Okay, the bottom, the minimum height of the rider is 1. The maximum is 17. And equilibrium is going to be at 9 feet. Okay, so let's run through all of our values here. D is going to be 9. That's where equilibrium is, so our vertical shift is 9. We don't have a phase shift, so C is going to be 0. Our amplitude here is 8, right? Because half of 16 is 8, and the distance between 9 and 17, or 9 and 1, is 8. So our A value is, it's not actually 8, it's actually negative 8, because we have this negative cosine function going on. So we need to have that reflection in our equation. So we need to make sure we've got a negative 8 there. And then finally, To find b, we'll do 2 pi over b equals the period. We know the period is 3, so we're going to multiply both sides by b and then divide by 3. So our b value is 2 pi over 3. There we go, 2 pi over 3. Okay, so now we got everything we need here, right? I think so. I don't think we're missing anything. So we can go ahead and write our equation. Y equals -8 times the cosine. In this case, it's cosine because we're starting at a minimum. If we're starting at a maximum, like this one up here, or if we're starting at a minimum, we'll use cosine. If for any reason we're starting at equilibrium, we'll use sine. So cosine of 2 pi over 3x. In this case, we do have a vertical shift. Our vertical shift is 9, so I'm going to have a +9 out here to the side. And just to kind of clean this up a little bit, let me put the equation up here. That's it. That is our equation for number 3. If I can grab this, if it'll let me, what I like to do is just box this up here. Or not, whatever. All right, so close, so close. Make it a little bigger. Yeah, this is not really helpful. Okay, there we go. All right, that's good enough. Okay, so there's our function. Here's our graph, and we're done there. Okay. All right, let's do the next one. A pendulum is swinging as shown below. Its horizontal displacement varies sinusoidally with time. Assume the pendulum is at 0 displacement at 0 seconds. So 0 displacement, that means we're going to be at equilibrium. That's our indication that we're going to have a sine function. The pendulum's maximum displacement is 17 and swings through a cycle of swings through 1/2 of a cycle every second. So if it takes 1 second to do a half cycle, one cycle, I'll type this out, one cycle would be 2 seconds. So that's going to be what our period is. Now I'm just noticing now this does not say if we're going up or down. Doesn't say which way it's swinging. Anyway, there's some missing information here. So I'm gonna throw it in there. Okay, so I'm gonna just make an addition here. Make a little note to fix this for next year, but if you're watching this in the future, I probably already fixed it. But for 2021, let's fix this problem and say something like the pendulum. Can I spell pendulum? Oh, come on. Initially swings toward positive displacement. Positive displacement. So without that information, in other words, what I'm trying to say here is it's going to go up to the positive displacement before coming back. It doesn't really, nowhere in here, unless I'm just totally missing it, but I don't see where it says which way it's going to swing. So this is some missing information that I'm just going to share with you here. If you were confused, I totally understand because there's not enough information here. Though really the only difference, though, if it were to swing the other way, is we would have a negative sign graph instead of a positive sign graph. So the only thing really different with our equation would be the a would be negative instead of positive. But I'm going to include that little bit of information so that we can stay consistent with everybody else and go ahead and show a positive sign graph. So what this tells me is that my a value is actually going to be positive. If I can draw this. There we go. Okay, looking okay here. I really don't like that I missed that little piece. But like I said, I'll go back and fix that. No biggie. All right, so we're going to start at 0. It says the maximum displacement is 17 inches. Okay, so we're going to label this 17. This one will be negative 17. And we said earlier that, oh, I didn't spell cycle right. Silky. No, cycle. There we go. Yeah, so if a half cycle, so, if I just make it to here, that would be a half second. So I'm sorry. half of the cycle is 1 second, so the other half would be another second, so the total cycle is going to take 2 seconds. All right, geez, this one's a little tricky, yeah. So 0 to 2. We're going to use that to calculate B, but let's write everything else that we have so far. Our amplitude's 17, and it's going to be positive because we have a positive sine graph going here. Our B value, we'll calculate that last. C value is 0, and D is 0 as well. So 2 pi over B is going to equal the period, which in this case is 2. So we have 2 pi equals 2B. 2B or not 2 pi? Is that the question? No, I don't think that is. And so B here is just pi. All right, so we've got everything we need to write our equation. So let's go ahead and start writing it. So we've got 17 times the sine of pi x, and that is all. All right, we don't have any horizontal or vertical shifts, so that's the complete equation. Number 5, your fishing bobber oscillates from waves in a lake where you fish. Your bobber moves a total of 1.5 inches from the high point to the low point and returns to the high point every 3 seconds. Okay, so this problem's kind of like the one we did in the notes. This particular diagram is not helpful at all, except for showing you what a bobber looks like. But it gives us nothing to work with here. In fact, I'm kind of offended by the fact that this picture is even here, because it does not help at all trying to figure out what's going on here. Can I make a white color here? I don't even know if it'll let me. Yeah, here we go. Here we go. We're just gonna get rid of this photo. Give us some room to work here. Because look at that. I mean, that's just like a piece of clip art. It's not helpful at all. Okay, anyway, enough of that nonsense. Let's dig in here. So basically, you've got a wave. Here's the wave, and you've got a bobber that's bobbing up and down. It says, sketch a graphic modeling motion if the bobber is at its high point and time equals 0. So it starts up here, and then the wave goes, and it goes down, and then back up, and so forth. So we're going to start at a maximum and go all the way down to the low point of the wave, and then go back up to the high point of the wave for our cycle. And it says that the bobber moves a total of 1.5 inches from the high point to the low point. So that means that our amplitude is going to be half of that, which is 0.75. So we'll label this as 0. We'll put 0.75 over here, and our minimum displacement will be negative 0.75. Oof. All right, and how long does it take to do that cycle from the high point to the low point back to the high point every 3 seconds? So there should be a 3. Okay, so a value here will be a positive 0.75. And the reason why it's positive is because we're starting at a maximum. We got no phase shift. Like I said before, I don't think there are any here that have a phase shift. And then our vertical shift is also 0. Let's calculate the B value. 2 pi over B, which is our period, is equal to 3. So we multiply that over, and we get 3B equals 2 pi. And then divide by the 3, so we get 2 pi over 3 is our B value. All right, so let's go ahead and write our equation. We've got y equals, we're starting at a maximum, so we're going to use cosine. So 0.05, you could write it as a fraction if you want. It doesn't matter. Or decimal, 0.75, 3/4, same thing. Cosine of 2 pi over 3. Oh, I guess I could have just done that. There we go. X, and then we got minus 0 plus 0, so none of that changes. Whoa, whoa, whoa. Let's move this. I'm just going to move this over here, make my answer box a little bigger, and then hopefully we'll be good for that. So that's it for number 5. Hopefully you're seeing that these can go pretty quickly as long as you know what to look for. So really, like, the key points here are going to be, what's the amplitude, what's the period? Where do you start? Do you start at maximum, minimum, or equilibrium? Okay, so there's number 5. We got one last problem here. Donna uses a rope swing to swing back and forth over a stream. So another problem, all of these are kind of similar to the ones we did on the notes, so hopefully you can kind of follow along with those. But anyway, it says it takes Donna half a second until she reaches the middle of the stream, which is 8 feet from her current position. Okay, so basically, if equilibrium, or the middle of the stream, like right here, is 8 feet away. So here's 8. We'll call this -8, okay? And she's going to swing back and forth like this. Okay, assuming Donna begins at maximum positive horizontal displacement. Okay, so that's over here. Write an equation and sketch a graph to represent her horizontal displacement from the middle of the stream. So this is another one where we're starting at the maximum. Were they all at the maximum? No, we had a sign actually, and this one was a minimum. I guess they weren't all maximum, but it looks like most of them are. So maximum displacement would be 8 feet from equilibrium, from the middle. There we go. So we'll just say equilibrium 0. The positive maximum displacement is 8, so we're going to put -8 down here. It looks like I'm going to have to actually move all this up at least a tad bit so I can label that horizontal axis. Okay, so for the horizontal axis, we're going to start at 0. And how long does it take? It takes 5 seconds until she reaches the middle of the stream. So for her to get from here to here is 5 seconds. So, or not 5 seconds, but 0.5 seconds, half a second. So to get all the way across, that's going to be 1 full second. But the period is 1 full cycle. And so to complete the cycle, we have to go back as well. So that means that the cycle is going to end after 2 seconds. So it's a half second, another half second, and another half second. All right, so that is, I think that's everything we need. Now we can go ahead and start filling these out. My A value here will be 8, and it'll be +8 because I'm starting at a maximum. My B value, I'll come back to that, solve that over here. And then my C value, no phase shift, so that's 0, and my vertical shift is also 0. So to calculate the B, we're going to do 2 pi over B equals 2, and I think we already calculated that one, didn't we? Yeah, we did. Number 4 had the same calculation. So we know that B is going to be pi. You could still solve it. I mean, it doesn't hurt to go through the solving process, but we do get pi for B. So our equation is going to be 8 times the cosine of pi x, and that's all she wrote. All right, well, that's it for today. Hope you guys are getting the hang of this. We will start working on our project next time over this unit, and I'll see you then. Y'all have a great day.